In the last video, we developed a TCP proxy in Python that allows us to now analyze the network protocol of the game. I think the code we have written is a really good example of why you should know programming when you are interested in IT security. While it does require some experience in coding, in the end it was not much code, and the result is that we now have a fairly powerful tool on our hands to reverse engineer the network packets. So for now, we don't really have to touch the main proxy code and we can focus on the parser function that we can play with. This function has 3 parameters, but the most important one is data. This is where the TCP payload that either the client or server sent comes in. In last video, we also implemented some filters here to only look at data sent by the client to the game server. And our tool is so powerful because we can now do anything in here, and whatever we change here will affect the output of the proxy. So let's get started. At the end of last episode, I already hinted at this one packet that doesn't change when we stand still, but changes in some parts when we move around, and also changes in a different part when we jump. So let's collect some test data. We see no data changes when we stand still. When we walk forward or backward, we see some changes, some left and right walking, then also jumping up and down. And notice that I didn't move the camera, so now also some looking around. Which area of the data was affected by what action was pretty obvious, but we need to analyze this very accurately. So let's copy out some samples into our script and look at them. So what can we see here? First of all our actions that we did were about moving around. And that packet is also the one constantly being sent. So it's really not a surprise and doesn't take much guessing that that will somehow contain our position. We can also quickly see that there seems to be 2 bytes at the start that are fixed. Then when we're walking around, data changes in this region and also back there. So this was forward and backwards walking. The walking left and right here is very similar, just the other byte here at the end is changing. This is perfectly consistent with our X and Y position in the world. Just to make it clear, of course X and Y is changing when we walk forward and backward or left and right, because it's unlikely that we are aligned to the axes. In that case, the movement would only change one coordinate. But what is bothering me a little bit is that the data that is changing is 14 hex digits, so 7 bytes. That's an odd number. We would expect like 8 bytes, 4 bytes per coordinate or something like that. But let's continue with jumping. Let's take out the 2 other packets. You see, they are longer and have a different ID, so let's deal with that later. When we jump, essentially moving up and down on the z-axis, only this value changes. And this is 8 digits or 4 bytes. As you know, this is a hex dump, a hex representation of the raw binary data of the packet. So 2 hex digits are 1 byte. And cutting the data here also now seems to indicate that the previous 2 values should indeed add up to 16 digits, so 2 times 4 bytes. That would also make much more sense. The last test was looking around and there only 4 bytes in the back are changing. Now we can try to label everything with a guess what the data could represent. We have a constant ID that I think means this is a position packet. We have probably X, Y, and Z coordinates, as well as some kind of looking around data. 2 constant 0 bytes and then something that indicates which key we pressed. Cool. So let's implement the parser for that. I will be using Python struct a lot, which can unpack different types of raw binary data. So let's start by unpacking the packet ID. To do that, we simply call struct unpack with capital H as a format character, which indicates we want to interpret 2 bytes as an unsigned short integer number. And you see how cool it is to just write something, save the file, and see the changes. This way it's super easy to learn more about the data. So here is the integer number in regular base 10 of our first 2 bytes, but when we print it as hex, it's not quite what we expect. We expected to see 6076, but instead we got 7660. So this is now a question of how you want to interpret the raw bytes, either as little endian or big endian. For the packet ID it doesn't matter, and I think it is a bit more comfortable to read the ID when we say it's 6076. So let's change it to big endian indicated by the greater than sign. Cool. We will probably get a lot of other packets later, so I thought it would be a good design to define a handler for different packets. So I create a Python dictionary with one element so far, and that is supposed to be a function. So hPosition is a function that will get the data as parameter. Oh, and also a no operation function would be cool. Bear with me, it makes sense in a second. Because now we can simply try to get the function defined in the handler for a given packet ID, and if it doesn't exist, the default value, in this case the no-op function, will be returned. And then the function is given the data starting after 2 bytes, so we cut off the packet ID because now we selected the correct function to handle the data. Maybe we implement an unknown packet output in the no-op, and then we can also test that. So this output is coming from inside our position handler function. But when we jump and we get these other packets we haven't looked at yet, we see an unknown packet message. Cool. Now let's carve out the X, Y, and Z position. Each of them are 4 bytes large, so it could be a signed or unsigned integer or a float. Now if we look at the data again, we see that it changes quite dramatically, even though we moved just a little bit. If it were an integer, I would suspect much smaller changes. So maybe it's a float? But in the end, it's just a guess and you can quickly test it. If the output makes sense, it was probably correct. If not, then try something else. But I think float is absolutely a reasonable assumption here. So we can write X, Y, and Z and get the value of struct unpack. By the way, if something returns multiple values in Python, you can automatically unpack them into individual variables like this. So our unpack will unpack 3 floats indicated by FFF, which would be 3 times 4 bytes, so 12 bytes. And then we can print the data nicely with float format modifiers to only show 2 digits after the comma. Now, the moment of truth. Let me hit the save button. Amazing, look at that. Now let's move around a bit in game. And yeah, the data changes reasonably. And when we jump or fly, we see that unknown packet for the jump, and we see the Z value change. Amazing. We reverse engineered part of our first packet. Now to be honest with you, I'm not sure how the looking direction could be encoded, as it's also 4 bytes, but it must be more than one number. But I ignore it for now. Let's do the easier stuff first. How about we have a look at the jumping packet? That's an unknown packet for us right now. Again, let's collect a few samples and format them so we can try to recognize patterns. One thing you might already notice is that when you press space, then you send a 1, and when you release space again, you send a 0. Oh, and by the way, the packet ID is missing here because we cut it off when we handed it to the no-op function where we printed the data. So we can extract that 1 byte with the struct unpack using the B format string for 1 byte and print it along the remaining data that we don't know what it means yet. And we can test it again. We jump a bit and here we go. So what could the remaining packet data mean? Wait, isn't that the packet ID of our position packet? The length of the data would also match. Oh, so the network protocol is not just sending a single packet with information every time when something happens, it might bundle multiple packets together. So when we jumped, it sent jump information together with position information. This means we have to change some stuff of our parser. You can do this in many different ways. I choose to just return the data that doesn't belong to the current interpreted data. So for example, for the jump handler, I cut away the first byte and return anything starting with the second byte. For the position, it's a bit more tricky. We have to quickly count how many bytes that is. So that would be 20. So I cut away the first 20 bytes. And for no-op, let's just cut away a single byte. Now we have to place our parsing into a while loop, where we always check the length of data and we constantly change data to what the handler function returns. And at some point, the parser has fully consumed the data. Let's continue reversing more packets with the same methodology. But I also think I want to make some changes to the code. Like I said multiple times, it's an explorative process, and so our tools develop with us once we figure out new stuff. So I decided to comment out the position print so we don't spam the output so much. And we do not print unknown packets in the no-op function, but instead check if the packet ID is defined in the handler, and if not, we print the packet. I noticed another unknown packet when switching the weapon and when shooting the fireball. But isn't it weird that we see slowly consuming unknown packet data by our loop when we shoot a fireball, but not with the weapon switch, even though both are unknown packets? Well, if you look closely, then you see that the weapon switch is also just 1 byte indicating the selected slot, which is consumed by the no-op. And then after that, we find the packet ID of the position packet again and fully parse that. Cool, huh? So let's quickly create a handler function for weapon select, which is basically like the jump handler, just a byte. Cool, another packet reversed. Now, what's going on with shooting the fireball? Let's take an example packet shooting the fireball, static link, and the remote exploit sniper rifle, and then compare them. One really odd thing is that the fireball packet is long. Before that, all packets had a defined size. So how do we know that fireball is larger than static link or sniper rifle? So the first 2 bytes are again the packet ID, so we know this must be indicating that we are using a weapon or spell. And then we have what looks like a byte with a value that is always different, hex 10, hex A, hex D. Then comes the 0 byte, and then what looks like the start of some data, and that data is very different. Though when you peek at the end of the packet, you notice that they are the same. So let's try to line that up. Oh, that is another position packet. We didn't move between shooting, so we know how to parse that data and can ignore it. When looking very closely and comparing the packets, I noticed more similarities. It's here starting with 82B and ending in 535. And lining that up looks like this. Because we know that a position packet would start here after these two 535, we can conclude that that is definitely an end of another packet, which means this 6672 is another small 1 byte large packet. And static link is like jump, an action that can be started and held for a bit and released again. So it's probably related to that. Let's create a short handler for that. Then back to our weapon data. At first I didn't know what that part stands for, but when I looked in another direction and fired another fireball and compared the data, I noticed that this part changed. So that's probably also some kind of shooting direction data. But still, how do we deal with the different length packets? Well, we know there is a number at the start that is different for all 3 of them. The largest one is hex 10 and is also the longest packet. Then comes the second longest packet with hex D and the shortest one with hex A. And when you count the bytes, it suddenly makes sense. This is the length. There are 10 bytes, here are 13 bytes, and here 16. And the trained eye might have also already recognized that that is ASCII text. When you read a lot of hex values, for example, because you play too much CTFs and spend time in debuggers, you start to recognize when data is text. It's just a skill you develop over time. So let's implement that handler. First, we extract the length. I assume that the length is actually not just a single byte, but a short, so 2 bytes unpacked with H. Then we know that the name starts after the second byte up to the length. We can use our awesome proxy to immediately test that. When we shoot something, we see the name. But of course the data parsing is still missing the last 12 bytes of data. So we don't really know how to interpret the direction yet. Might be the same as the position data, rotation or looking direction, but we just ignore it for now and return the data after all of that. And then we test it. We get a beautiful output when we are using a weapon. And also you can see now very well how the static link is toggled on and off depending on how long you hold the mouse button. Awesome! We just parsed a variable length packet. Before we end, I just would like to mention something. Maybe you find it weird how I so quickly understand how to parse that data. But you know, there are not that many options how it can be done. If you ever think about how you would implement it on this low level, then this is pretty much the only option you have. You know the basic data types like integers, floats, ASCII characters, and out of these you build more complicated structures. And then there are also typical, intuitive, and very obvious techniques such as type length value encoding. And this is pretty much what we had here. The packet ID is indicating the type of data, so like a weapon shoot type, and because of the name that can have different length, we need also something that tells us the length. And then the data itself. You just have to think about it a bit, and then I think it's super obvious. At least when there's no additional crypto or compression layer involved. See you next video where we explore some more things with the proxy.